curvature of a curve is a measure of how quickly a tangent line to the curve is turning. So for example, we could consider the curvature of the curve y equals x squared from the points P to Q. So we can imagine tangent lines to the curve at P and move the point P towards Q, and we could observe how the tangent changes. We would see that the curvature as we move from P to Q would be greater than if we move from, say, point Q to point R. So the tangent lines as we move from point P, Q to R don't change too much. Here we have a circle. Well, if we pick 2 points that are a certain distance apart on the circle and consider the curvature, we will get some value, a measure of how quickly the tangent lines are turning. But if we picked 2 other points on the circle that are the same distance apart as the first 2 points, we would find that the curvature is the same. So the curvature is the same everywhere on a circle. Let's consider 2 circles of different radii centered at the origin. We could look at the curvature of the inner circle as the tangent lines turn from point P to point Q. We could also look at the corresponding curvature of the outer circle as tangent lines turn from point P prime to Q prime. P prime and the origin are on the same line, and so is Q prime and the origin. Now let's look at the tangent line to the inner circle at P. Now it's a fact that a tangent to a circle is perpendicular to the radius line from the center of the circle to the point of contact of the tangent. At P prime we have a tangent line, and again that's perpendicular to the radius line from the center of that circle to the point of contact of the tangent to it, which is P prime. So both of these tangent lines are perpendicular to this radius line. So that means that these tangent lines are parallel to each other. If they're parallel to each other, they cut off the same angle on the x-axis. So the slope of these 2 lines is the same. Let's call the angle that they make with the positive x-axis psi. So the slope of these lines will be the tan of psi. Now, if we take the inner circle, as point P moves to point Q, this tangent line will turn through a certain angle, and when we get to Q we will have this tangent line here, and we'll have this angle made here. So let's just call this dot. Similarly for the outer circle, this angle here will be dot. Notice however that for the inner circle the tangents turn through a smaller distance for the given change in the angle. So the angle changes from psi to dot as we turn the tangents over a smaller distance. Now the distance between 2 points along a curve is called S. Now we could imagine a tiny increment of that distance, say from point P to this very close point, nearby point. We can call this increment ds. So for this given increment the angle will change by a certain amount, which we will call d psi. Now we could consider the change in the angle d psi divided by the increment along the curve ds. We could also do that for the outer curve. We could imagine the same increment ds. So these 2 increments have the same size, the same length, but d psi for the outer curve will actually be less than it will be for the inner curve, because we have to cover a greater distance along the curve here for a given change in the angle. So as we go from P to Q on this curve, or from P prime to Q prime on this curve here, the change in the angle is the same. It's just that we have to go a greater distance here for a given change in the angle. So just to reiterate, for a given ds for both curves, ds is the same in both, d psi, the change in the angle for the inner curve will be greater than d psi, the change in the angle for the outer curve. So we have a tighter turn here, so the tangents are changing more quickly. If the tangents are changing direction more quickly for the inner curve, then the angle is changing more quickly for the inner curve than for the outer curve. So we use the quantity d psi ds for what we call the curvature of the curve. Well, actually we use the magnitude of d psi ds, and we denote it by the Greek letter kappa. Now normally our curve has an equation of the form y equals f of x. We don't have an equation involving the distance s along the curve. So we need to rewrite d psi ds so that we can involve derivatives involving x. Well, d psi ds can be written d psi dx multiplied by dx ds, so the dx's will cancel, or that's the same as d psi dx divided by ds dx. Now if we write d psi ds like this, we still have to deal with the derivative ds dx, so we'll have to get ds in terms of dx and dy. Now before we get limits, let's look at delta x and delta y. In the limit these will become dx and dy. So delta s is a small increment of distance along the curve. If delta s is small enough, then that distance along the curve delta s can be approximated by the straight line distance between the endpoints of the arc. The horizontal distance between the points is called delta x, and the vertical distance is delta y. So Pythagoras' theorem tells us that the straight line distance between the endpoints of the arc is the square root of delta x squared plus delta y squared, and we can of course square that. We are after ds dx, remember, so we can divide all of this equation by delta x squared, so we get a 1 here, and then take the square root. Next thing, we take the limit of this quantity as delta x goes to 0. As delta x goes to 0, delta s over delta x becomes ds dx. That's what we're after. And as delta x goes to 0, of course delta y will also go to 0, and delta y over delta x becomes dy dx. So that's ds dx found. So our function is y. We can also call it f of x, so dy dx can be written df dx, or f prime of x. We need to square it, add 1, and take the square root. Now we see that d psi dx comes into our formula for the curvature, so we're after d psi ds ultimately. But let's see how we can get at d psi dx. Well, the tangent line at our point on the curve makes angle psi with the positive x-axis. And we know that the slope of a tangent line to the curve at x is just the derivative of the function at x. It's just f prime of x, or dy dx. Now the slope is also given by tan of psi, tan of the angle the line makes with the positive x-axis. So df dx or dy dx or f prime of x equals tan of psi. Now we could start with this equation here and differentiate both sides with respect to x. If we differentiate the tan function, we get sec squared, and by the chain rule we need to differentiate the argument psi with respect to x. But sec squared psi is identical to 1 plus tan squared psi, and the tan of psi is the slope of the tangent to the curve, which is the derivative of the curve at x. So now we can write d psi dx in terms of the first and second derivatives of the function with respect to x, in terms of f prime of x and f double prime of x. That's what this thing here is. So f double prime of x divided by 1 plus f prime of x squared will give us d psi dx. And to go back to the curvature again, we know we have to divide d psi dx by ds dx. So here's d psi dx, and we need to divide it by ds dx, which is this thing here. So we have to multiply this denominator by 1 over this thing. Well, we have to multiply it by 1 plus f prime of x squared to the power of minus a half. So we will get a power of... Actually, I'm sorry, we have to multiply this denominator by this quantity here. So we just add the powers. We have a power of 1 here, power of a half here. So we get 1 plus f prime of x squared to the power of 1.5, or to the power of 3 halves. And that's our formula for the curvature of a curve at x.